Hey, in this video I'm going to introduce you to object-oriented programming, which is what we'll focus on heavily throughout the rest of the module C++ 102. This is going to be a high-level introduction and overview of some of the topics that we'll discuss in this lesson, but also in other lessons throughout the rest of this module, so don't worry if at first you don't understand all of the topics. We will go through them again and in more detail in the relevant lessons and in the relevant lectures. To get started, I want to recap what we've talked about before in the module C++ 101, particularly in the lesson on functions. A function, also called a routine, a procedure, and a few other things, is basically a named reusable block of code. Now, the programs that we wrote in the module C++ 101 were procedural programs, right? That was really the focus of that module. You have these programs that are basically collections of functions. You declare your variables and then you pass those as arguments to functions. Now, sometimes a procedural program is all you need, especially for small programs. Let's say you want to process some file, you want to process the input and sort of change that, mix that around a bit and produce an output, or calculate something, right, do some mathematics. But as the program grows in size and complexity, and especially if you want to model real-world things, then procedural programs won't work because they can become difficult to maintain, extend, reuse. Right, it's really important with programming that we can reuse our code, not just in the same program, but sometimes we want to write libraries of code that we can reuse across multiple projects. So code reuse is important, and procedural programs can also become difficult to understand and thus also to debug. Of course, if a program is difficult to follow or to understand, then naturally it becomes difficult to debug as well. Another negative point is there's no real owner for the data. It'll either be local to some function or it'll be global, right? This can lead to data integrity issues where some functions can inadvertently modify that data, and where we fix a bug in one algorithm that may lead to bugs in other places. As a simple example, let's say we want to model a player character for our game. Then we go and declare a bunch of variables, let's say in the main function. We want to keep track of the health of the player, the armor, and maybe how much cash that player has. Maybe they can buy things in-game, such as a role-playing game, for example. So we have those variables now, and to print them out and to do things with them, we use functions. So that's great. We can do some functions such as void print player stats. Then we can pass those variables in as arguments for this function. So I have a health parameter, an armor parameter, and a coin parameter. The coin parameter is of type float. There are a few problems with this. For example, let's say we want to change the coin variable from type of float to a type of double. Not the parameter, but the actual data type, so the variable that we declare in main, for example. You change that from float to double. Of course, you pass a double in as an argument to this player stats function. Then you'll have a possible loss of data warning, unless you do casting, right? Also, what if we want to add an additional attribute that the player can have, such as mana, or an equipped boolean variable to keep track of whether or not the player is equipped with a weapon, for example. Now we'll have to go and update all of the functions to include these new attributes, such as the print player stats. And of course, this is only one function. You can have multiple functions that will either modify the state of your character, such as whether or not it is taking some damage, maybe you're losing hit points, or health in other words, or coin, right, maybe you spend some money in-game to buy a new weapon. This means you can have many functions that operate on these stats that make up the particular state of your character as you go through and play your game. What we would prefer to do is to wrap all of these statistics, or in other words the attributes of the player, and the functions that operate on that data together, right, or in other words to encapsulate all of that together. And that is really where object-oriented programming comes in. Here's a quick example of an abstraction or model of what a player character would look like, and the attributes and functionality that the player character can have. This is basically a custom or a user-defined variable type that we can create instances of, just like we can create instances of integers and floats and so on. As you can see, you'll have fewer parameters to deal with since the member variables are directly accessible to the member functions of the class. The members are basically owned and managed by the class. If you want to make a change, such as if you want to add an attribute for your character, then there will be fewer changes that need to be made than with procedural programming. This is easier to maintain, extend, and debug. Next, I want to talk about data modeling, which is the process of creating a representation of entities and the relationships between those entities for a predetermined problem domain. Now, of course, the problem domain is going to be the program that we want to write, the scope and the abstractions that we have to write for that program. Let's say we want to create accounting software or model some sort of bank account system. Then the entities will be the different banking accounts that you can have, such as a savings account, a check account, and so on. A data model or abstraction basically has 4 building blocks: an entity, which is a noun, a person, place, thing, concept, or event, for which we can store data. An entity represents a type of object, where each occurrence, also referred to as an instance, is distinct. Then the attributes are the characteristics of an entity. Now these are the member variables or data members that are encapsulated and bind to member functions within your entities. Then you have constraints, which are restrictions placed on the data to ensure data integrity. We'll talk more about this as we go along. You also have relationships between those entities. So in C++, we are concerned with inheritance and composition, or is a and has a relationships. I actually have an entire lesson dedicated to inheritance. And then also from time to time, I'll use entity classes and structs as examples. Instead of giving the class or struct a specific name, I'll call it entity. In the case where I present some abstract or high-level concept or idea, and we want to focus on specific C++ features. We model entities with classes and structs in C++ because those are basically the same. There are some minor differences which I'll discuss in the relevant lessons, but a class or struct is a code blueprint containing member variables defining its state, and member functions defining its behavior, in other words what it can do. We basically encapsulate the member variables and the member functions to ultimately create that entity or abstraction. Before we move on, let's talk about encapsulation in a bit more detail. As I mentioned in the functions lesson in the module C++ 101, to reuse code we encapsulate it, meaning we put the code in a named self-contained block of code. Now in object-oriented programming, encapsulation refers to the binding of data members and the member functions that operate on the data members. And encapsulation leads to data hiding, where we can specify access rights for the members through special access modifiers. We can basically modify the access rights of some members to be public. In other words, those members, whether they are variables or member functions, can be accessible to outside code, or in other words, to code outside the class. And we can also make some members private so that they are only accessible by member functions of the same class. The idea with data hiding is we only allow data member access through public member functions. In this way, we don't allow direct access to the data members, but instead you have to gain access to those through functions, and in some cases we don't actually want to allow access to some variables at all. In other words, typically your data members will be private, and to get the values that are stored in those, or to modify those, or in other words to write to those, you will do that through public functions. This allows us to do certain checks in the functions to make sure that we only modify the data members as planned, so we don't get weird results. For example, let's say we have a health or a hit point variable, an integer, and if that health variable is 0, then it means the character is dead. If it is 1 to 100, then it means the character is still alive. But based on gameplay testing of the particular game or the game design document, the health cannot be more than 100 and it can also not be less than 0. Based on that, you want to do certain checks. Let's say you pick up a medipack and you gain 50 health when you already have 80 health. Then again, you want to make sure to set your data member, your health data member, to 100 instead of 130, for example. Let's say we have this player character class and we encapsulate the member functions, get health, set health, and the data that those functions will operate on, so in this case an integer health, into this class called player character. Now with this we also have an example of constraints, which are again restrictions placed on the data to ensure data integrity. For example, the get health and the set health member functions are public and are accessible from outside, but the private member, the health member, is only accessible from within inside. In other words, only the get health and set health member functions have access to that private member. I would like to mention that you can also have private helper member functions. These typically assist other member functions in performing their function, but it's not necessary for those to be accessible outside the class. A class is like a blueprint of a house, and that blueprint specifies where the walls will go and so on, but on a per instance basis, so each house that you actually build using that blueprint, you can paint the walls a different color. The owner or the guy that actually builds the house might request certain changes in the internal layout of the house and so on. So it's just a plan, but it can be customized slightly, right? You get the idea. And when it comes to programming, the classes are similar in that they are a high-level plan or idea. The main difference is a class is for logic. It will specify the variables and the functions in that plan, so the states and the behaviors that you want that class to have by default. Here's a simple example of the class concept. When you go into programming, you consider on a high level what it is that you want to create. So in this case, we want to create a door for our game. The class might be called door, and by default we assign it a color of yellow, health of 50. Let's say the door can be destroyed, kicked down or something like that. We have functions with the parentheses in that bottom section. Those are functions. So the door might take damage. If health reaches 0, the door is destroyed. Another function that you might have that you can call that says open door. And if you call that function, the door will open. Again, that is some behavior that this thing can do. Alright, so you have this high level idea or class, and then you can create instances, right? You can instantiate that door. In your world, you can have doors like all over the place. Each one of those might be slightly different, so you can have different colors and so on. Door instance 1 might have a color of red, so you go and create a door instance, and on that particular instance you change the color of that door to red. You might set the health as well to 120, so it'll take you a long time to break that door down, when you're trying to run away from the zombies. Then door instance 2 I might change to green. You can see I don't specify a health here, so in that instance we'll get the default value for that variable that was set in the template, so in this case 50, right? So each instance will have the defaults that are set for that class unless you go and change that. Similarly with door instance 3 I change that to blue, and in this case I also change the health. Again, just a quick example, you have the high level idea, which in this case is a door for our game. It has various states, it has variables and functions. Alright, and from that class we create instances, and on those instances we can make changes to the state. As a recap from these user-defined classes or structs, we can create variable instances with preset, in other words default, or dissimilar states. Also note that class or struct variable instances are referred to as objects in C++. As an example of object instantiation, you can see in the main function, we are familiar with this type of statement already. In X, we declare a variable instance, or in other words an object, of type int. Those are the fundamental types, float, double, and so on. Now we can also declare variable instances of our custom user-defined types. Let's say we have a user-defined type called struct name or class name. Then we specify that type just like you would int, float, and so on, followed by the name, in this case demo instance, just like you would specify an identifier or a name for variables of the fundamental types. Now remember that member variables and member functions are encapsulated within our user-defined classes and structs, and you might be thinking, how do we access those? Because those will be contained within the instances. Well, that is where we will use member accesses. So in this example, we do that demo instance.x using the dot operator to access the member x, which will be a member variable defined within the struct. And of course you can also access functions, so we do the dot operator followed by the function. Now for us to access the members in this way, they need to be public. You also have an arrow member access operator, which we'll discuss when we talk about pointers in the next lesson. So again, don't worry about this too much, we'll discuss this in more detail as we go along using actual examples in Visual Studio. In terms of modeling relationships in C++, we have inheritance, and I'll show you a couple of quick high-level examples. Let's say we have three classes, class A, class C, and class B. Each class or struct will have their own members, right? Whether those are member variables or member functions. Now let's look at an example of inheritance. In this example, class C inherits from class A and class B, meaning that class C contains the members of class A and the members of class B. And of course you can extend class C to make it unique, so you can add its own members. For example, class A can have some container within it, such as an array, an integer array, along with the functionality to print those members out and to get or set elements within that array. Class B may be a completely abstract class, in other words we cannot instantiate that class B, but it may contain useful functions. So for example, we can overload, or in other words modify the existing operators such as the stream insertion operator, including other operators actually such as addition and so forth. Operators are basically implemented as functions, but let's say we want to modify the stream insertion operator to work with our custom classes, and instead of coding the functionality for each and every one of our classes to work with the stream insertion operator, so that for example we can do cout, the stream insertion operator, and an instance of one of our objects, right? That's a lot of repetition to go and implement or overload that particular function for each and every one of our custom classes. So instead we can inherit from an abstract class, where at least some of that functionality exists already. Okay, some pros and cons with object-oriented programming. Reusability is a pro for object-oriented programming because we can reuse existing code in derived classes, or in other words in inheritance hierarchies, and also across multiple projects. That again is because our classes and structs basically encapsulate data and the operations that you can perform on that data. So in other words, data members and member functions. And once tested and basically validated, we can reuse that code across multiple projects. In object-oriented programming, we can also write more abstract or generalized code, where the programmer is not concerned with how the functionality is implemented. They can simply use it. We also have data ownership, so some variable is owned and managed by some object, and the code is easier to extend, test, debug, and maintain. There are some negatives though. For example, it is a steeper learning curve, right? We have to learn about object-oriented programming, inheritance, and all of those things. More design or modeling is required for entities and relationships. Basically, you'll do more planning and design before you actually write the code, and programs can become large and complex. You're not just passing data around, you also have to now think about relationships between data entities. Okay, this was just a high-level introduction to object-oriented programming and some of the concepts that we'll study throughout the rest of the module. Some of the important points I mentioned is abstraction, the idea of writing generalized code, encapsulation, and information hiding and ownership. Also talked about entities and the relationship between entities, so inheritance, which is basically where we create new abstractions based on existing abstractions. This is great for reusability, so we can derive new classes from existing classes. Basically, the child class will use the members and the functionality that it inherits from the parent. Of course, this means we don't have to rewrite that code each time. We can just use code that already exists. And in some cases, we might want to modify that slightly, and that's fine. C++ allows for us to do that, and I'll explain how to do that, where we can basically override functions from the parent class. I also hinted at operator overloading, where we can define versions of existing operators to work with our user-defined types, so in other words, our classes and structs. That's also an important topic, and I have an entire lesson dedicated to that. Okay, that is going to wrap up this overview, and in the next lecture we'll talk about structs and how we can actually define and instantiate those. Now I'm doing it in this way because in the next lesson on pointers and references, I want to show you some examples using structs, because I want to show you some of the seemingly complex syntax that you get. So that's why I'm covering structs before pointers and references.